I like to cover the topic of gas here. And gas has three subtopics. They are properties of gas, gas law, and ideal gas law. In this particular video, we'll focus on the gas law, the Charles law mainly. Let's begin by looking at this image. In this image, you'll see molecules inside of a container that is movable, meaning that the volume can be adjusted. Now, I introduce heat under here. Well, what do you think is going to happen to these gas molecules? They're going to move and they're going to hit the sides of the wall of the container, causing this disc over here to move up. So it increases in volume. Okay. Now, say you have this increased volume with gas and you introduce a bunch of ice. So you're cooling this entire container down. Well, the molecules will no longer hit the sides of the wall container. They will, but not as much as if you were to heat it. So the molecule starts to come closer and closer together, causing the volume to also diminish. So with this, we can say that there is a direct relationship between temperature and volume, in that when temperature increases, the volume increases. When the temperature decreases, the volume decreases. We can come up with Charles' law with this particular equation. VI over TI is equal to VF over TF. In other words, VI is initial volume, TI is the initial temperature, TF is the final temperature, and VF is the final volume. And that temperature, it must be in Kelvin, no Celsius, no Fahrenheit. I like to demonstrate this by showing you a can demo. Let me explain what just happened there. So you had a can, and that can had water molecules, and that water molecules were all gas. Initially, it was just liquid water, and then what I did was I put it under very high heat, and so heat was added. So molecules started moving around and then it went into gas phase, and there were a bunch of gases, water molecule gas there. Yes, there's some escaping, but not as much. There are some do escape, but there are a lot inside as well. And it takes up all the space within this container, right? And then soon as it was submerged into the ice water, what happens to the water molecule? Well, the water molecule all come crashing down together and they feel the coolness. So what happens is it'll bring down the volume with it. So hence why the can crashed. This shows that when temperature decreases, the volume also decreases as well. And it really shows that through this can demonstration. Let's do a learning check. A sample of gas at 15 degrees Celsius and 1 atm has a volume of 2.58. What volume will this gas occupy at 38 degrees and 1 atm? So let's see. Let's do some setup here. So initial temperature was 15 degrees Celsius. The pressure initially is 100 atm. It also has an initial volume of 2.58 liters. What about T final? It has increased its temperature to 38 degrees Celsius. The pressure is the same, 1.00 atm, and it's asking for what volume. So I want to know what T final is. Since the pressure is exactly the same initial and final, we don't need to really look at the pressure. So instead of having it there, I'm going to go ahead and erase that. It's not confusing. So we have temperature and volume, and we can use the Charles law. So let's go ahead and use the Charles law. Charles law says that VI over TI is equal to V final over T final. So I want V final to be by itself and everything on the other side. So I'm going to multiply T final both sides. And T final then cancels out. So I have V final is equal to T final times V initial all over T initial. Great. Now we can plug everything in, but just before you plug it in, remember when we're using the Charles law, in fact, all of the gas law, you can't use Celsius as the temperature. You need to convert the Celsius into Kelvin, Fahrenheit also into Kelvin. So you're going to add 273.15 for both of the temperatures to get it into Kelvin. So let's go ahead and do that for the first one and second one and come back. So those are my two temperatures. Let's plug them in. 311.15 Kelvin. And then we have our volume initial, which is 2.58 liters. Then all over the temperature initial, which is 288.15 Kelvin. Let's go ahead and plug this into our calculator here. So we have 311.15 times 2.58. Okay, hit enter and then divide that by the initial temperature, which is 288.15. And I get 2.79 liters. And Kelvins cancel out, so we're left with liter. And this is good because you see how the temperature has increased, right? From here, it has increased to over here. And you see the volume also increased, not significantly, but it did increase. In the next learning check, I'd like for you to go ahead and read and set up the equation, set up the initial and the final first before you plug them in. Then we'll come back and plug them in together. So hopefully you're here. Now we're going to let T final to be by itself. Note that the T final is on the denominator. Here's a little trick. When the T final or whatever you're looking for is on the denominator, the calculation can get a little bit more complicated than if it's something that you want is on the numerator. So here's a little trick. You're going to flip everything so that temperature is on top and volume is on the bottom. Now solve for T final. Multiply V final both sides. That will cancel out the V final. And we have T final is equal to V final times T initial all over V initial. If I were to plug this in, we have V final as 3.82. T initial is 279 Kelvin. It's already in Kelvin, not in Celsius, all over V initial, which is 3.00 liter. All right, let's calculate this out. 3.82 times 279. Hit enter and then divide it by 3.00. And I get 355.26 Kelvin as my T final. I like to keep it as consistent in 3 sig figs, so reduce it to 355 Kelvin as my T final.